Hi everyone, my name is Farhin Ahmed. I'm a postdoctoral researcher at the Laboratory for Auditory Neuroscience and Development as part of the Bloedel Hearing Research Center in the University of Washington, and I'm working with Dr. Bonnie Lau. Today I'm going to present my talk on decoding the infant brain, neural predictors of language and learning difficulties in neurodiverse population. Now, speech and language are one of the most fundamental skills that we develop as human beings. From the moment we are born, we start learning how to listen, respond, and eventually talk. The skills grow rapidly in early childhood, starting from our infancy to toddlerhood, and they're critical not just for communication, but also for learning, social development, and emotional connection. However, not all children reach this milestone with this expected trajectory. Many children, especially those with neurodevelopmental conditions, experience delays or difficulties with speech and language acquisition. In the United States, about 1 in 31 children has autism. About 1 in 700 babies are born with Down syndrome. 75% of autistic children exhibit some degree of speech and language impairment, while 95% of children with Down syndrome exhibit some form of speech and language impairment. And these challenges don't just mean that they're struggling with words. It means they are being impacted how they interact with the world and form friendships and access educations. So understanding and supporting their communication need early on is vital for their ability to thrive. However, with the existing protocol, speech and language impairments are often not diagnosed well after their third birthday or sometimes even later. And with factors such as lack of awareness, socioeconomic status, difficulty getting appointments for professional assessment make it even worse. And importantly, the traditional assessment protocols are prone to bias because they rely heavily on structured questionnaires or interviews that are often biased by a caregiver's report or by an examiner's interpretation. And so we are striving to answer two questions here. Number one, can we push the limit of early, say as early as when the baby can't even talk? I know this is ambitious, but we just don't want to wait and watch and lose 2 or more years of their precious lifetime doing nothing. And number two, can we be more objective so that we can minimize human subjectiveness that comes along with the traditional developmental assessments? And we think the answer could be in neurotechnology, such as electroencephalography or EEG, that allows us to non-invasively look into the brain. So this can help us by allowing us to listen to the infant brain before they can speak, and by offering objective data-driven brain-based measure that are unbiased by human judgment. And that leads us to listening to the brain by leveraging something called the neural tracking of speech envelope. So envelope is the fluctuations in the amplitude of the speech waveform. So the blue here is a typical speech waveform and the red trace is its envelope. Human auditory cortex consistently reacts to changes in the speech envelope, which is called the neural tracking of speech envelope. And this is a known phenomena in adult literature, something that has been replicated over many, many studies using EEG or MEG. Now we grew from bring infants to adults. That's the direction of natural development. However, in the field of human auditory neuroscience, this development has been in backwards. The reason I'm saying this is because although this neural tracking phenomenon has been discovered over 2 decades ago, only very recently studies have started looking for this in infants and kids. Now, realize that adult participants have many years of listening experience, so it has been a long-standing question whether this phenomena exists in pre-verbal infants who have not yet developed their speech and language-related skills. So Kalashnikov et al. Provided the first evidence of neural tracking of continuous natural speech in pre-verbal 7-month-old infants in 2018. And since then, there have been 5 more infant studies. And I'm highlighting the years here just to emphasize that these data are coming from very recent years. And all of the studies reported significant neural tracking. So this phenomenon is something, is an ability that emerges very early on in human life. However, a major research gap here is that most of the studies have been conducted in neurotypical infants, so we don't know how this phenomena emerges in neurodiverse infants. So to test that, we have EEG data from infants born with Down syndrome and infants with high likelihood for autism. They are called high likelihood for autism because they have a sibling in the family with confirmed diagnosis of autism. So they are also at an elevated likelihood for developing autism. These infants came to our lab. They sat on their caregiver's lap and listened to 12 minutes of natural continuous infant-directed speech, such as, "Hi, baby, do you like bubbles? I like bubbles," this fun and engaging speech materials. And we recorded their 128-channel EEG data. We had total 64 infants in our data set, 22 in the DS group, 42 in the HL group, either at 6 or 12 months of age. Then we use the temporal response function decoding model. This model derives a mapping between stimulus feature, which is the envelope in our case, and the EEG through regularized linear regression. With this mapping, we can reconstruct an estimate of the speech envelope, assess its correlation with the actual envelope, and report it as the reconstruction accuracy. To derive the chance level performance of the model, we use a non-parametric permutation-based approach. We use a subset of our data to train this model and use the left-out data to test the model. So with this approach, using 1 to 8 hertz EEG, the left side shows the reconstruction accuracies derived from the model, and the right side shows the chance level performance of the models. As you can see, we could successfully decode the speech envelope from the brain activity for both DS and HL group at both 6 and 12-month-old. So we do see neural tracking of speech envelope inconsistent with what have been found in the neurotypical infant studies, which is a good news, which means that then we can use this metric as a potential biomarker. Next, we looked for potential differences between delta 1 to 4 hertz and theta 4 to 8 hertz tracking, since stronger delta tracking was observed in neurotypical infants compared to theta band tracking. I'm not showing the chance level performance here, but all of the models performed better than chance at both delta and theta level. And we found that in the HL infants, delta tracking is stronger than theta band tracking at both 6-month and 12-month of age. However, in the Down syndrome infants, delta tracking is stronger than theta tracking at 12 months, but not at 6 months, so we see some differences here, which requires further investigation. And finally, we looked into their brain behavior correlation with the question that can the neural tracking measure at 6-month and 12-month of age predict behavior in the second year of life at 24-month? Using this formula, we modeled this relationship, and we have some Vineland parent report and Bailey for infant-led measures for a part of our samples. These are standardized behavioral assessments performed in the clinics, and we found that their reconstruction accuracies at 12 months significantly predict behavior from those standardized tests that was administered at 24 months of age. All right, so to summarize, we found evidence for neural tracking of natural speech in pre-verbal infants born with Down syndrome and high likelihood for autism. We saw preferential tracking of delta band over theta band and some age-related difference across groups there. The neural tracking measure at 12 months was significant in predicting many behavioral outcomes at 24 months. And together, this suggests that this neural measure can be robustly detected in neurodiverse infants and can be used as an objective biomarker. Now we know that EEG is cheap, portable, and easy to use. So we envision that this brain-based measure can someday be added to their routine screening so that we can move from waiting and watching to early evidence-based action. With that, thank you so much for listening. If you have any questions, you can email me at farhin@uw.edu. You can connect with me on LinkedIn if you're working on a similar topic. And please scan this QR code to visit our lab website to learn more about our work. Thank you so much again.